This video is on the different transformations that exist. This primarily pops up in grade 11 and 12 math. The video is just going to focus in on what is all the terminology of transformations and what type of transformations actually do exist. So our four transformations that exist are a horizontal translation, a vertical translation, we have reflections either about the x or the y axis, and then we have horizontal/vertical stretches. So those four combine what we call transformations, and they're how we can alter graphs. And you're going to see that a lot below as we go through each of these. So starting with horizontal translation, we have y is equal to f of x minus a, and that's its general form. And that a is the units that the function shifts by, so either right or left, just depending on what the problem is. So let's do a quick graphic example below. I have the right half of the function x squared, so it's a parabola shape, but I'm only dealing with the right-hand side of it. So we can see in the gold, we have the original function here. And then I say, well, what if we want to do a horizontal translation 1 unit right? Well, then the function becomes x minus 1 squared. And so that seems a little strange. We're going right, but it's minus 1. Shouldn't that go left? Well, let's just focus on that here. Why is the sign opposite? In our general form, why is it that y is equal to fx minus a? Well, let's do a quick study on our basic function y, or f of x is equal to x squared. So we have the same type of function, and we've outlined it the exact same way, where we're going to shift it by 1 unit right. So it's still that x minus 1. But what's really going on here? We can actually see this through our table of values of what's going on with our two functions. We clearly, if we want to maintain the same y value for each point, aka just shifting the graph left or right, then we don't want to change the y values. So obviously, what we're going to have to do is, if we look at our table of values here, we see a 4 and a 4, we see a 9 and a 9, and a 16 and a 16, and a 1 and a 1. Do we see how for each of those original values, their y value is 1 lower than it would be on the x squared graph? So what I mean by that is, for each of the ones that occur in this x squared column, the same value occurs 1 lower. So we know that this proves that x minus 1, well, technically that means we need an x value that's 1 greater than, hence why we shift it to the right to maintain the same y value. Next, we're dealing with vertical translations. So the general form is this y is equal to f of x plus b. B is the units the function shifts by vertically. So yet again, we have the basic function f of x equals x squared in the gold here. And this one is a lot more simple because we don't have any opposite signs going on. Our extra unit, or the one that it shifts by, is just an extra number on the end here. So whether that's positive or negative, as we can see at each of our point of our original gold graph, in the example given here, we say we have a vertical translation of 1 unit upwards. So that just means that each point on the graph is just going to go up 1 from its original, 1 from its original. And same with on this side, it'd be 1 for each of those. So that's pretty easy to understand, because then if we had a negative, it's just going to be shifting down by b units, the same on each of those points. What about reflections, either horizontal or vertical? So this one's going to make sense after it's explained, but we have to really key in on the terminology that's being used here. So for the first one, we have a vertical reflection. Well, that's just putting a negative in front of our f of x. And how does this make sense? Well, if we have a vertical reflection, we're saying that it's going to shift over that x-axis. What was originally our top function here, so we're going to say, in the first case, this was our original function, the f of x equals x minus 2 squared. But if we're shifting it over the x-axis, aka we're reflecting it vertically, then we should expect to see a function that points down instead and is the opposite way, vertically. So that's why we say it's going to be a reflection about the x-axis, because we're reflecting over the x-line here. Similarly, if we deal with our general function for horizontal reflection, we have y equals f negative x. And so this is a horizontal reflection about the y-axis. We're reflecting over that y-axis. we have our original function in blue here, and then we're taking all those values of that function and flipping them over the y-axis to get our function on the other side. So it's just a mirrored image. In both of these cases, a reflection is technically just taking the original function and mirroring it over the given axis, depending on what type of reflection we're dealing with. And finally, we have horizontal and vertical stretches. So specifically, let's start with the horizontal stretch. We have our original function, which is the f of x squared. So that goes back to the function we were dealing with before. And now it says, if we have our general form, which states that our stretch occurs by a factor of a here, then if we put a 2 within the brackets as an arbitrary example, then each of these values is immediately going to scale by 2 right away. And then with a vertical stretch, we're doing the same kind of thing, except we're performing the function initially. So we have our x being squared. So whatever x value we plug in, that's going to be squared right away. It's only attached here. Whereas before, the 2 and the x were combined together, then we squared it. In this case, we have an x that's being squared first, then multiplied by the 2 outside there. So that is the subtle difference that occurs between the two of those. And even in their general forms, you can see right away that there's an a on the interior versus an a on the exterior for a vertical stretch. And so what's really happening, because these look really, really similar. If we look at our before and afters for both of these, do you notice how the red line, which is our after line, looks very similar to the red line on the horizontal stretch? The horizontal stretch and the vertical stretch kind of look the same. Let's see what's really going on here. When we look at our table of values for specifically the horizontal stretch first, which is this one here to start with, our horizontal stretch is represented by this table and our vertical stretch is represented by this table. Well, when we look at our horizontal stretch, the pattern that's going on here is that for whatever x value it is, it has to be half the x value in order to get to the same value. So what I mean by this is that with a horizontal stretch, if we start with, or if we have 4 originally and that's going to give us 16, then to get that same 16, we now have to have it as a 2 instead. So it's actually half the x values. And so when we say that what's going on here, it's actually listed as, if we had this exact same setup, we have y is equal to 2x in brackets squared. Well, this is a horizontal stretch by a factor of 1/2. And that seems strange because you're thinking, oh, well, didn't the graph grow? Like, didn't it go a lot higher in the red? The after graph looks like it got really high. But what was happening at each of the x values? Specifically, if we started at 1, 1, now we're at roughly about 1/2 and 1. So our x values have actually cut in half, but our y values have grown exponentially in this case. So that's why when we deal with the horizontal stretch, we can say that it's actually a horizontal stretch by a factor of 1/2, even though it's listed as this 2x within the brackets. We can't be fooled. We have to say it's the opposite of it. Similarly, the direct comparable I would say to this is that when we're dealing with our horizontal translations, we said that an x minus a, well, if this is actually a negative, so for an example, an x minus 4, this is a shift right. So we actually have to think about it in the same way. It's opposite of whatever is listed. With our vertical stretch, this should make sense because all the values are being doubled. So whatever they were before, our 2 coefficient, or the part here, should immediately say that if we're stretching all our values vertically, that means that for every y value we originally had on our blue graph, so for every for every point that existed on this blue line, those are all going to get stretched by a factor of 2 or double what they were. So as we can see, we have 4 and 8, and then 9 becomes 18, and then 16 becomes 32. Do we see how they're all being doubled? So we would say in this case, there is a vertical stretch by a factor of 2. And so it's not opposite like it is for horizontal stretch.